So in this video we use determinants to ascertain or determine whether a matrix has an inverse or not. So the previous video we saw that the matrix inverse A inverse is defined as 1 divided by the determinant of A times the adjoint of A, and the requirement was that the determinant of A not be equal to 0. And remember, we previously have said if the determinant of A, just write it like this, is equal to 0, then we say that A is a singular matrix. Singular. This was from a previous video. And then we said if it's not singular, then it's non-singular. So you're either singular or you're non-singular. And a non-singular matrix was one for which the determinant was not equal to 0. So it's going to be precisely the non-singular matrices for which this formula works. If it's singular, if the matrix A is singular, the determinant of A will be 0, and we would get a division by 0 if we tried to use the inverse formula. So the corollary of this, and in math when we use corollary, what we're saying is something follows easily from a previous result. So in the previous video, the proof of this formula for A inverse actually spanned 2 slides, and I suggested to you that you should take 15 to 20 minutes to read it and try to understand the proof. When we have a corollary, what we're saying is the previous result, the previous claim and proof were perhaps difficult, but what follows easily from it is a new claim. So what you'll see is we have this corollary: a matrix A is invertible if and only if and only if the matrix is non-singular, and by non-singular we mean the determinant isn't 0. And what you'll notice is that the proof of it, which you should read, is very short. It's short, it's easy, and it's easy to understand. It's a corollary. There's no hard work that needs to be done to come up with this claim here, the corollary to the previous claim. So what we can do is take advantage of this corollary here to determine whether matrices are invertible, and so the utility behind this is, why bother trying to calculate the matrix inverse if the matrix inverse doesn't exist? And again, it's all driven by the fact that the determinant has to be something other than 0 for this formula to work. So here, for example, if we take the determinant of this matrix A, we get 2 times 2. Right, I'll write it out. 2, 3, 1, negative 2. We find the determinant. We're going to go 2 times negative 2 is negative 4, minus 3 times 1 is 3. This equals negative 7. And because the determinant isn't 0, the inverse exists. And it would make sense to try to calculate it. Here, if we calculate the determinant of B, we get 6, 2, 3, 1. We get 6 times 1 minus 3 times 2 is 6, equals 6 minus 6 is 0. So because the determinant of this matrix B is 0, B inverse does not exist. B inverse does not exist. And we could play the same game one more time. We could say, hey, what's the determinant of this matrix? So the matrix C has determinant. Let's expand the determinant in terms of row 3. So it'd be plus minus plus, so it's going to equal negative 1 times the determinant of the minor matrix that you get when you eliminate column 1, row 3. So that's going to be 4, 12, negative 3, and negative 7. And then the 0 will 0 out the next minor, so we get plus minus, we get to ignore this, and then plus, so plus 1 times the determinant of the minor that you get when you strike out row 3, column 3, which is going to be 2, 4, 4, 12. So when we run the calculation, we get the opposite of 4 times negative 7 is negative 28. Minus a negative is going to be plus 36. Plus 2 times 12 is 24. Minus 4 times 4 is 16. So here we're going to get the opposite of negative 28 plus 36 is positive 8. So we get the opposite of positive 8 plus 24 minus 16 is 8. The determinant is 0. C inverse does not exist. There's no point in trying to calculate it. If the determinant is 0, inverse doesn't exist. If the determinant isn't 0, if we have a non-singular matrix, then the determinant exists.